In this video, let us find the center of gravity of a solid cone. A cone is a common structure which we see more in our day to day life. For example, a conical flask in chemistry lab, funnels used in our kitchens, caps used in a birthday party, or more common examples which we see in our daily life. For a solid cone, the picture, the first picture explains the best. So it is a wafer in a conical form filled with ice cream is the perfect example to explain a solid cone. See, a conical structure will have a pointed tip and its base will look like its base will look like a flattened circle. So let us take one solid cone, and in the picture it is drawn as an inverted cone and its section has been drawn as A, B, C. A is its vertex and this BC represents the base of the cone. The height of the solid cone from the vertex is taken as h. Since the base looks like a circle, its radius is r. And joining A and D will give us the height, which is more technically called as the altitude of the solid cone. Now what we are going to do is, we are going to slice the cone into many parts. When you slice the cone into many, you could see these many layers. So each slice will look like a disc. So the top, from top to bottom, you could see many discs with varying radius. At the top, the radius is less. As we go down, you could see the radius is increasing. Let us consider one slice named in this picture as B1C1 from the vertex A at a height at a distance x, and the thickness of this disk B1C1 is dx, and the density of the solid cone is taken to be rho here. See in this picture, the disk B1C1 has the radius as y, and the angle between this altitude AD and the side AB is alpha. Draw a perpendicular line from B1 to E. Now you can see this A1 B1 E represents a right angled triangle. I have taken this right angle or drawn this right angled triangle separately. So you could see this A B1 E representing a right angled triangle. I am going to find out tan alpha from this right angled triangle. A tan alpha is given by opposite side by adjacent side. The side opposite to angle alpha is B1E, which is y, and the adjacent side is AE, which is x. So y is equal to x tan alpha. And we know the volume is calculated as area into thickness. Now we want to find the what is the volume of the slice we can B1C1 we considered. We know volume of the slice is, or a volume is given by area into thickness. So area is for a circular object is pi r square. The radius for the disk is y, so it's pi y square. Its thickness is dx. Just now we found the value for y, so so it is pi x tan alpha, that is y is equal to x tan alpha. We have substituted as and simplifying we get pi x square tan square alpha dx. Then we need to find what is mass. To know the mass, we are making use of density is equal to mass by volume. A product sign has been mistakenly typed here. So the density is equal to mass divided by volume. From that we can easily find out what is the mass. So mass is equal to density into the volume. To find the mass of the disk, we have density and volume computed here. So the mass of the disk dm is equal to pi into x square tan square alpha. The whole square alpha is has been uh, um, mistakenly typed here. It is pi x square tan square alpha dx into rho. Now let us find the distance of the center of gravity of a solid chrome from its from its vertex. So the formula is x bar equal to integral of 0 to h x dm divided by integral of 0 to h dm. We know the value for dm. Now let us substitute it. So substituting, we get integral 0 to h x pi x square tan square alpha into dx into rho. See, in bracket the whole power square has been mistakenly repeatedly copied. So the brackets to the square will not come. So it is simply x pi x square tan square alpha into dx rho. In the denominator also the same, integral of 0 to h pi x square tan square alpha dx rho. The whole power square will not come. So the terms within the bracket pi tan square alpha rho or constants, so it has been taken out pi rho tan square alpha, and in the denominator also same pi x tan square alpha we will get. So that's pi rho tan square alpha in the numerator and the denominator will get cancelled. The remaining left is integral of 0 to h x into x square dx divided by integral of 0 to h x square dx. So simplifying, we get integral of 0 to h x cube dx divided by integral of 0 to h x square dx. So when we integrate this x cube, we get x power 4 by 4 between the limits 0 to h, and in the denominator we have x cube by 3. That is, when you integrate x square, you will get x cube by 3 between the limits 0 to h. So applying the limits, we get, so the lower limit is 0, which is not typed here. The lower limit is 0. So we will be applying only the upper limit. When you apply the upper limit, we get h power 4 by 4, the whole thing divided by h cube by 3. When you rearrange and write, you get h power 4 divided by 4 into 3 by h cube. So this h power 4 and h cube will get cancelled. The resulting will have 3 by 4 h, x bar equal to 3 by 4 h. Therefore, the center of gravity of a solid cone along its axis is at a distance of 3 by 4 times its height from the vertex A.